Hi everybody, I'm Martin Zimmermann and I'm going to present you joint work with Aniello Murano from Napoli and Sasha Rubin from Sydney on optimal strategies in weighted limit games. So the problem we are considered with in this work here is so-called reactive synthesis. So let me start you by giving you a toy example of this problem. So imagine we have this grid of cells and two robots. The blue one, this is our robot, and the red one, which is antagonistic. And the goal is for the blue robot to reach the cookie up here without being caught by the red robot. And you can see on this grid, we have some obstacles here, so some mountains, we have some lakes and some leaves. And the interaction between the two robots works as follows. They alternate moving, and in each move they can move to some other cell. So for example, let's say the blue robot, our start, could go to the right, trying to get to the cookie, but then the red robot comes down to prevent us from doing that. Now we go this way, continue, and the red robot tries to get us by going around the mountain. Now our robot just jumps over the lake. Now we see we are in an advantage because now we can move only one field here. And then the blue robot is the first to reach the cookie and thereby satisfies its specification because it has reached the cookie without being caught by the red robot. Okay? So in general, you could imagine more relevant problems that could be modeled in such a way. And the general problem one considers in reactive synthesis is the following. You model the interaction between an agent you want to get an implementation for and its environment as a graph. And on that graph, you play an infinite duration two-player game. And the specification you're interested in yields the winning condition of the game. Okay, I will give you an example in a second. Let me just mention before that we are then interested in computing a winning strategy for the player representing the agent we are interested in. So in our example, the blue robot. And such a winning strategy for this game can be seen as an implementation for the agent that satisfies the specification. Okay, so again, let's look at an example. For our robot example, we would construct a graph where the vertices encode a state of this grid, so the positions of the two robots. And we have two types of vertices, the round ones that correspond here to the agent we're interested in, so the blue robot, and the square vertices where it's the turn of the environment, which here controls the red robot. And now you can see here at this, say, initial vertex, the agent, the blue robot, can either go right or up. So we have exactly two successor states, one way the robot went right and one way he went up. And then it's a move of the environment, which can move the red robot either to the right or down, and so on. So the full graph is much bigger, so I can't draw it on the slides here. But what we now do is, this infinite duration game is played as follows. We place a token at the initial vertex, and then the player whose turn it is moves the token to some successor. So here, the circle player, also called player 0, moves the token to either this or that successor. And then it's the turn of player 1, the square player, who moves the token to some successor here. And thereby we build an infinite path through this graph, sometimes called an arena, and this gives a play. And now the specification just tells us which plays are winning for player 0 and which ones are winning for player 1. And what we're interested in is a strategy, that means a recipe that tells us how to move the token in a way that we enforce a win. So no matter what the other player is doing, we only produce paths, plays that are that satisfy the specification. Okay, This is a general setting of the problem we're interested in. And now, this problem has been studied since the late 60s already, and a lot of work has been done. Let me just mention one thing that is important for the work here. Oftentimes, you have a qualitative specification, for example, reach the cookie, but these qualitative specifications often have quantitative aspects. So you could, for example, try to optimize the time it takes you to reach the cookie. This might be under the influence of your opponent, who could maybe force you to take a bit longer, depending on how the opponent plays. But you want to minimize the worst case time it takes you to reach the cookie. So what that means is there's a preference order among winning strategies and thereby implementations. We are interested in computing optimal winning strategies. This is the problem we consider here. Not only any strategy that satisfies the qualitative specification, but one that satisfies it optimally according to the quantitative aspect we're interested in. And oftentimes what this means is we have to put weights on the edges. So for example, this could mean this move here costs us 3 units of energy to do, and this one here is more expensive. It takes 20 units of energy. Or this could also be time or some other cost, and we want to minimize that cost here. Okay? So for example, jumping over the lake might be more expensive than going around it, but takes less time, so that might be preferable. And now let's talk a bit about specifications and winning conditions. So the most basic one is the one we use in the example, the reachability condition. So the qualitative aspect here is to reach a fixed set of vertices. In the example, the ones where you got the cookie for the blue robot. And the quantitative aspect could, as mentioned, be minimize the accumulated weight along the edges through the graph. And this problem has been solved before, and oftentimes as a special case of more general problems. And what is known is that optimal strategies exist in any game, and they can be computed in polynomial time if the arena is finite. Okay? But not everything is a reachability specification. So another foundational class of specifications are the so-called recurrence specifications. Here the goal is to reach a fixed set of vertices infinitely often. So it's not enough to eat one cookie. If you want to survive forever, you have to eat infinitely many cookies. And now one quantitative aspect one could consider, and this is the one we consider here, is to minimize the maximal accumulated weight between such visits. So we see this fixed set of vertices infinitely often. We eat infinitely many cookies, but we want to minimize the time we are hungry. Okay? And this problem can be encoded in a wide range of more general problems as a special case. And we have a long list of such more general problems in our paper. But they do not yield a fine-grained analysis of the complexity of the problem, and in particular not of the values of strategies and the size of strategies you need to implement these optimal strategies. So what we do here is we provide this fine-grained analysis of the problem. Okay, so after this motivation, I have one slide of formal definitions, and then mostly results and some examples. So this is the most technical part here, so bear with me. What we do here is we want to separate the size of the arena, which models the interaction between the agent and its environment, and the specification, which will be just an automaton. And this gives a more refined complexity analysis, because we separate the arena and the specification. Oftentimes they are just put into one graph by taking a product, but we don't want to do this here. So we need some definitions for that. We say if we have a language of finite words, K, then the limit of that language is the set of infinite words over the same alphabet such that there are infinitely many prefixes that are in K. Okay? So infinitely often you are in K. And if K is, for example, the language of words where the last vertex corresponds to eating a cookie, then the limit of K is the language of infinite words where infinitely many cookies are eaten. Okay, now we say that a weighted regular limit game is a structure comprised of an arena A with weights, where we use natural numbers as weights for the edges. E are the edges of the arena A. And we have a winning condition of the form limit K for some regular language K over sequences of vertices of the arena. So the interaction between the two players is given by this arena A, and the winning condition will be given by a DFA for this regular language K. Now we need to define the value of a play. What we do is the following. Rho is a sequence of vertices. So what we do is we look at every position j in this sequence, and then look at the next one that is strictly after that, such that the prefix up to that position j prime is in K. And then we look at the weight from our position j up to j prime. So intuitively, we look at the longest stretch starting from a position where the prefix is in K up to the next one where it's in K. This is equivalent due to monotonicity and the fact that we only use non-negative weights. Okay, and then we take the supremum over all positions to pick the maximal such weight. Okay, I will have an example in a second. So, and now we lift the value of plays to strategies for player 0 from a vertex 3 by just taking, again, the supremum over all plays that start in that vertex and are consistent with the strategy. So, again, a worst case analysis. What's the worst my opponent can enforce against that strategy? And now we say that a strategy is optimal. So sigma is optimal if its value from every vertex is not larger than the value of any other strategy, sigma prime. Okay? So for every starting vertex, sigma gives you an optimal value. There's no better strategy from that vertex. And notice that this is a uniform definition. The strategy has to be optimal not from only from one vertex, but from every vertex. Okay. So what we're interested in is showing that optimal strategies exist, and if they do exist, that we can compute them efficiently, and furthermore, what kind of properties these optimal strategies have. So let's have a look at an example as promised. So here is our arena. Notice that I don't use vertex names, but I use labels. So A, B, and C are labels here. And the automaton just processes these labels and not vertex names. But you could easily give these vertices name and let the automaton produce the corresponding vertices with that label. It's just more easily readable if you have these labels. So the arena is rather simple. You can stay at these self loops at the A-labeled vertices, or you can go on, see a B-labeled vertex, and then go further to another A-labeled vertex with a self loop. And you can do this several times until you see a C, and then you go back. And all these edges have some weight W, but for this back edge, which has weight 0. Okay, so in particular, notice that only player 0 moves in this arena, so we don't have any vertices for the opponent, which means we can identify strategies with plays. So if we are interested in finding a strategy from this vertex, say we only have to construct a single play, and this is a strategy. Okay, so this is the interaction between the players. And this here is the automaton for the winning condition. Remember, you have to have infinitely many prefixes that are accepted by this automaton. So that means infinitely many prefixes have to reach this state Q0 here. So what that means is, from the initial state, you have to see 5 A's, a B, this takes you back to the initial state, or you have to see a C and then 5 A's and a B. These two things can happen. They take you from this state to the to itself back. And you have to see this C infinitely often to be in this accepting state infinitely often. For this game, this means essentially there's a unique winning play and therefore unique winning strategy, and this has value 18 times W, and it works as follows. You use every self loop 4 times. That means you have seen 5 labels A, then you see a B, then you're back in this state Q1 here, then you again see 5 A's and a B, you're here, and so on, until you see the C, and then you have to go back and do the same thing again. You cannot stay too long in this self loop because you cannot process 6 A's in a row, and you cannot stay in there too short because then you cannot process the B. Okay, so this is what's going on. Essentially, you have to use a self loop a few times and then see a B, use a self loop a few times and then see a B, and so on. And this has to be done ad infinitum. That's the only thing player 0 can do if she wants to satisfy the specification given by the automaton. Okay, so we will come back to this example later. What I want to mention now is that using or looking at the value of a play is, in a sense, a refinement of just looking at whether play or strategy is winning or not. So what that means is, if the value of a play is finite, then the play satisfies the specification, it's winning. And similarly, if a strategy has a finite value from a vertex, then it's a winning strategy for player 0. Okay, from that vertex V. And it turns out that both of these implications only hold in one direction. So the other one can easily be shown to be wrong. And there's an example down here where we essentially want to see infinitely many V1. And we measure the distance between the occurrences of this V1. And this just diverges. So if you see here, we have 2V0, then we have 3V0. Here we have 4V0 already leaving the screen, and so on. So this still satisfies the specification limit K. We see infinitely many V1, but the value is infinite. So having a finite value means you're winning, and you're winning in a very strong sense. Okay, there's this weak winning where you have infinite value, which is not so good from the quantitative aspect, but still okay from the qualitative one. And in that sense, having a finite value is a refinement of just winning. It's just better. And having a strategy of finite value is typically more desirable than having any strategy. Okay, so let's talk about our main results we've shown in the paper. First of all, we have shown that player 0 has an optimal finite state strategy in every regular weighted limit game. So as long as the game is finite, there is an optimal finite state strategy. Finite state strategy means you can implement it by an automaton with output, so it's a finite object. And furthermore, the problem, given a finite arena A and a DFA for the winning condition, compute an optimal strategy in the induced game. This can be solved in polynomial time, in the number of vertices and edges of the graph, and the number of states and accepting states in the automaton, where we use the unit cost model to deal with the weights on the edges. Okay? And from the proof of this result, the second result here, we get some upper bounds on the value of an optimal strategy. So notice that this could be infinite, but if it is not infinite, then it is bounded by this value here. So it's linear in the size of the arena and the size of the automaton, and linear in the largest weight used in the arena. And furthermore, we get an upper bound on the memory size of an optimal strategy. Again, linear in the arena and linear in the number of states and accepting states of the automaton. So at worst, quadratic in the number of states of the automaton, if every state is accepting. Okay, I don't want to explain you how to prove this. This is a fixed point characterization, a nested fixed point characterization, where the inner fixed point is for reachability and the outer then takes care of the recurrence. Have a look at the paper if you're interested in that. What I want to mention before I conclude is the matching lower bounds for these upper bounds we have proven on the value and the memory. So let's first talk about the lower bound on the value. Remember that the upper bound is essentially cardinality of the number of the set of vertices of the arena times the number of states of the automaton times the largest weight. And if you generalize this example here, you will get a tight lower bound on the value of an optimal strategy. Essentially, we have seen you have to repeat this self loop a number of times that is proportional to the number of states of this automaton. And for every 2 states, you have to repeat the self loop here. And each time you get a W. So by having more groups of these AB gadget here and more states in this line of A's, you get a bound that is roughly V times Q. Okay, so this is easy. We have seen this example before. So now let's talk about memory. And here I want to only give you a rough idea without going into technical details how we implement memory structures. Essentially, it's an automaton with output as mentioned before. And look at this game here again. So again, only player 0 moves, so we can identify strategies with plays. So let's have a look what's going on. Let's first look at this automaton. It says you have to see at least one A, and then either you go through this circle here, cycle, or you go to the accepting state. And now what's going on is, since we have 2 A's here, this means you have to go through this cycle. We start here, we see 2 A's, that means we have to go this way, and then we have to see a bunch of other A's. Then the B here, and then the C. So then we can go here. And now I notice that there should be a self loop here as well. So this one is missing. The Q state should have a self loop. And what's going on now is that if you check the weights here, if you start at the J's vertex here, you have to go to the J's vertex here. This minimizes the weight along the path. Okay? If you start at the lower one here, you have to get to the lower one here. If you start here at the first one, you have to get to the first one. Again, this is due to the weights along the edges, which are carefully chosen so that they add up to n+2 on each pass. Okay. Now, what's going on is, to implement this, you have to remember the index of your starting vertex, that's n memory states, and you have to use the self loop here a certain number of times, s-1 times. This comes from this automaton. And altogether, this means you need n times s-1 memory states. And this is tied up to a factor of f, the number of accepting states, if you remember the previous slide. Okay, so it's almost tied. Okay, so much for the second lower bound. So one of them is tight, the other is almost tight. And this concludes my presentation. Thank you for watching. If you have any questions, please ask them during the Q&A session of the conference, or afterwards. If you see this video after the conference, please send us an email. Our email addresses are here. Thank you.